Bismillahirrahmanirrahim. Assalamu alaikum. I am Nimran Naseem from the Department of BS Biotechnology and my ID is 22. And the topic of my presentation is the chemical effect, shielding, instrumentation, and the applications of nuclear magnetic resonance spectroscopy. So, first of all, let me start our presentation with introduction. What is NMR? Basically, NMR spectroscopy is a powerful analytical technique used to characterize organic molecules by identifying carbon-hydrogen frameworks within molecules. It is a technique that exploits the magnetic properties of nuclei. It determines the physical and chemical properties of atoms or the molecules in which they are contained. NMR gives information about the number of magnetically distinct atoms of the type being studied. When hydrogen nuclei are studied, for instance, one can determine the number of each of the distinct types of hydrogen nuclei as well as obtain information regarding the nature of the immediate environment of each type. The combination of IR and NMR data is often sufficient to determine completely the structure of an unknown molecule. Then our main topic, which is the chemical shift and shielding. Nuclear magnetic resonance has greater utility because not all protons in a molecule have resonance at exactly the same frequency. This variability is due to the fact that protons in a molecule are surrounded by electrons and exist in slightly different electronic environments from one another. The valence shell electron densities vary from one proton to another. The protons are shielded by the electrons that surround them. In an applied magnetic field, the valence electrons of the protons are caused to circulate. This circulation, called a local diamagnetic current, generates a countermagnetic field that opposes the applied magnetic field. And this effect is called diamagnetic shielding or diamagnetic anisotropy. Basically, in an atom, the local diamagnetic current generates a secondary or induced magnetic field that has a direction opposite to that of applied magnetic field as shown in diagram. As a result of diamagnetic anisotropy, each proton in a molecule is shielded from the applied magnetic field to an extent that depends on the electron density surrounding it. The greater the electron density around the nucleus, the greater the induced counter field that opposes the applied field. The counter field that shields a nucleus diminishes the net applied magnetic field that the nucleus experiences. As a result, the nuclear processes at lower frequency. This means that it also absorbs radio frequency radiation at this lower frequency. Each proton in a molecule is in a slightly different chemical environment and consequently has a slightly different amount of electronic shielding, which results in a slightly different resonance to frequency. So, what is chemical shift? The relative energy of resonance of a particular nucleus resulting from its local environment is called chemical shift. NMR spectra show applied field strength increasing from left to right. The left part is downfield and the right is upfield. Nuclei that absorb on upfield side are strongly shielded, whereas the nuclei that absorb on downfield side is weakly shielded. So, uh, this is a diagram in which di-shielded nuclei or shielded nuclei. So what is di-shielded nuclei? These protons sense a larger effective magnetic field so come into resonance at a higher frequency. And in shielded nuclei, these protons sense a smaller effective magnetic field so come into resonance at a lower frequency. So the electrons surrounding a nucleus affect the effective magnetic field sensed by the nucleus. This is downfield and this is upfield and frequency is toward the downfield. Shielded nuclei do not sense as large a magnetic field as di-shielded nuclei do. As a result, the energy difference between the alpha and beta states is much lower in energy for shielded nuclei resonant at lower frequency. So the di-shielded nuclei have a much higher energy difference between the alpha and beta states and these resonate at a much higher frequency as shown in diagram. So measurement of chemical shift. Basically, the standard reference substance that is used universally is tetramethylsilane, is also called TMS. Tetramethylsilane is placed in a solution of the substance to be measured and frequency difference is measured directly. This compound was chosen initially because the protons of its methyl groups are more shielded than those of most other known compounds. Thus, when another compound is measured, the resonances of its proton are reported in terms of how far they are shielded from those of tetramethylsilane. So, This is a formula. It is delta is equal to shift in hertz divided by spectrometer frequency in megahertz. This is the formula of chemical shift. For instance, at 60 MHz, the shift of the proton in bromomethane is 162 Hz from tetramethylsilane, while at 100 MHz, the shift is 270 Hz. However, both of these correspond to the same value of chemical shift, which is 2.70 parts per million. And this is a graph of NMR spectrum. So our second topic, which is instrumentation of NMR spectroscopy. So, introduction. Instruments that are used to obtain NMR spectra are usually named NMR spectrometer. A high-resolution spectrometer contains a complex collection of electronic equipment. NMR spectrometers are referred to as 300 MHz instruments, 500 MHz instruments, and so forth, depending on the frequency of RF radiation used for resonance. These spectrometers use very powerful magnets to create a small but measurable energy difference between two possible spin states. Protons in different environments absorb at slightly different frequencies, so they are distinguishable by NMR. The frequency at which a particular proton absorbs is determined by its electronic environment. Modern NMR spectrometers use a constant magnetic field strength V0 and then a narrow range of frequencies applied to achieve the resonance of all protons. This is a schematic diagram of NMR in which it is sample in tube. This is electromagnet which shows south and north pole. This is radio frequency generated, then detector and amplifier, and this is CRT displayer. So what are the components of NMR spectrometer? So first of all magnet, then field lock, then shim coil, then probe units, detector, amplifier and recorder. Magnet. The NMR magnet is one of the most expensive components of nuclear magnetic resonance spectrometer system. Sensitivity and resolution are critically dependent on quality of magnet. What is the features of magnet? It should give homogeneous magnetic field. For example, the strength of the magnetic field should not change from point to point. The magnet must be capable of producing a very strong magnetic field with strength at least 10,000 Gauss. Types of magnet. First type is permanent magnet. It is simple and inexpensive to operate but requires extensive shielding and must be thermostatic to 0.01 degree. Disadvantage. Field variation is not possible as it required because different nuclei resonate at different magnetic field. Second type of magnet is electromagnets. They are more effective than permanent magnet because of possibility of field variation, and they require power supply to produce magnetic field and cooling system to counter the heat generated from the electric power. They are operated at 12,140, 14,090 or 23,490 Gauss. Superconducting magnet, which is third type. A superconducting magnet has an electromagnet made of superconducting wire. Superconducting wire has a resistance approximately equal to 0 by immersing it in liquid helium at 0 degrees. The length of superconducting wire in the magnet is typically several miles. So the second component is the field lock. In order to produce a high-resolution NMR spectrum of a sample, there is a need of homogeneous magnetic field. The field strength may vary over time due to aging of magnet, movement of metal object near the magnet, and temperature fluctuations. So what are the types of field lock? There are two types. First, external lock system, then internal lock system. So what is external lock system? In this, an external reference nucleus is continuously irradiated at its resonant frequency and resultant NMR dispersion signal is continuously monitored. Second is internal lock system. In this system, a suitable reference such as tetramethylsilane is added to the sample. The analytical sample nuclei and reference experience the same field. An automatic shim coil control continuously compensate for the several magnetic field gradient. Third component of NMR is shim coils. The purpose of shim coils on a spectrometer is to correct minor spatial inhomogeneities in the magnetic field. These inhomogeneities could be caused by the magnet design, material in the probe, variations in the thickness of the sample tube, sample permeability, and ferromagnetic materials around the magnet. A shim coil is designed to create a small magnetic field which will oppose and cancel out an inhomogeneity in the induced magnetic field. Fourth component is probe unit. Probe unit basically comprises of four parts: sample holder, RF oscillator, sweep generator, RF receiver. So first, we'll discuss sample holder. Sample should be held in holder which should be chemically inert, durable and transparent RF radiation. Glass tubes of about 8.5 cm long and 0.3 cm diameter are employed. Glass tubes are embraced in order to protect UV-sensitive sample. Quarts of polyfluoroethylene sample cells are also available for photochemical studies. A spinner is provided to spin the tube at several hundred radiation minutes in order to make the sample experience homogeneous magnetic field. Second is radio frequency oscillator. To irradiate the sample with electromagnetic radiation, a highly stable crystal-controlled oscillator coil is imposed at right angle to the applied magnetic field. To achieve magnetic interaction of a radio frequency radiation with the sample, the oscillator coil is wound around the same sample cell. This is the radio frequency oscillator as shown in picture. Then sweep generator. For a nucleus to resonate, the precision frequency should become equal to the frequency of the applied RF radiation. This can be achieved by frequency sweep method. This method is used to resonate the nucleus. The frequency of the RF radiation is changed so that it becomes equal to resonant frequency or precision frequency. Second method is field sweep method. In this method, to resonate the nucleus, the frequency of the RF radiation is kept constant and the position frequency is changed by changing the applied magnetic field. So, radio frequency receiver. This is last component of probe unit. A few turns wire is wound around the sample tubes tightly. This receiver coil is perpendicular to both the external magnetic field and radio frequency oscillator, which is also called transmitter. When radio frequency radiation is passed to the magnetized sample, the resonance occurs, which causes the current voltage across the coil to drop. Now, let me discuss about the working of NMR spectrometer. Firstly, we will place the sample which may be resonating nuclei or atomic nuclei. So, in the sample holder can hold the sample. It has capacity to capture about 0.4 ml of liquid sample in it. Magnetic field can be generating by permanent magnet. Here you can see the poles of magnet that may develop. The first is south pole and the second is north pole. Basically, it is a permanent magnet. The NMR signals may be produced due to the resonance of atomic nuclei with radio waves. The radio waves can be produced by radio frequency transmitter. You can see radio frequency transmitter, which is also known as RF transmitter. It is used to produce a radio wave signal or pulse of radio waves. After that, the signal can be detected by RF detector and NMR signals can be amplified with the help of amplifier. You can also see amplifier in the diagram. After that, the readout system can be used. Here you can see the recorder, so that after using the readout system, we firstly use recorder to record NMR signals. Then we use NMR system, that is basically a computer device that can analyze the data and represent it, and that data give the organic structure of that specific sample that may present in sample holder. So we can also use sample probe to fix the sample in sample holder. The resonance frequency of an atom or a molecule is changed by the internal molecular magnetic field surrounding it. So it means that if we change the magnetic field, means if we change the homogeneous magnetic field into heterogeneous magnetic field, then the resonance frequency of an atom or a molecule will also be changed. So the resonance frequency gives detail of a molecule, individual functional group and its electronic structure. So, detector. This is the second last component of NMR spectroscopy. When radiation is passed to the sample, the two phenomena, namely absorption and dispersion, may occur. The observation of absorption or dispersion will enable the resonance frequency to be determined. There are two methods to detect the resonance signal. First is single coil method and second is double coil method. Single coil method, which is also known as radio frequency bridge. In this method, coil used for surrounding the sample serves as both transmitter and receiver coil. The applied signal is balanced against the received signal and the resonance signal is recorded as an out of balance EMF, which may be amplified and recorded. So the second double coil method, which is also known as nuclear induction method. In this method, there are separate transmitter and receiver coils. These two coils are fixed at right angle to each other as well onto the direction of external magnetic field. When no absorption of energy takes place, the detector coil picks up none of the energy given off by RF transmitter coil. When the sample absorbs energy, however, the reorientation of the nuclear spins induces an RF signal in the plane of detector coil, and the instrument responds by recording this as a resonant signal or peak as shown in diagram. Then last component is amplifier and recorder. The received signal is amplified by the help of amplifier and it is recorded by using a computer device. Then move toward our last topic, which is application. So this is the last picture of NMR spectrometer. Then applications of NMR, which is our last topic. So first of all, solution structure. The only method for atomic structure determination of biomacromolecules is aqueous solutions under near physiological conditions or membrane membrane environments. Second, molecular dynamics. The most powerful technique for quantifying motional properties of biomacromolecules. Third, protein folding. The most powerful tool for determining the residual structures of unfolded proteins and the structures of folded intermediates. Fourth is ionization state. The most powerful tool for determining the chemical properties of functional groups in biomacromolecules such as ionization state of ionizable group at the active sites of enzymes. Fifth is weak intermolecular interactions, allowing weak functional interactions between macrobiomolecules, for example, those with dissociation constants in the micromolar to millimolar range to be studied, which is not possible with other technologies. And the last is protein hydration, a powerful tool for the detection of interior water and its interaction with biomacromolecules. And hydrogen bonding, a unique technique for the direct detection of hydrogen bonding interactions. Drug screening and design, particularly useful for identifying drug leads and determining the conformations of compounds bound to enzymes, receptors, and other proteins. Metabolite analysis, a very powerful technology for metabolite analysis. Chemical analysis, a mature technique for chemical identification and conformational analysis of chemicals, whether synthetic or natural. So, in material science is a powerful tool in the research of polymer chemistry and physics. That's all from my side. Thank you.